This is AI with Justin. In the previous video of this series, I covered the extension of the restricted Boltzmann machine to the deep Boltzmann machine and deep belief network. In this video, I'll be explaining in more detail how multi-layered networks transform information and explore various forms of deep autoencoders and the tactics they utilize to form more valuable and reliable latent representations. First, let's overview the basics of a standard autoencoder. An autoencoder is a model composed of a graph of directed neurons which attempts to reconstruct the input it is given. We can make comparisons between an unfolded RBM and an autoencoder, minus the symmetry of the weights. An undercomplete autoencoder, what usually comes to mind when autoencoders are mentioned, is an autoencoder which has fewer neurons at some layer in the network than in other layers. This causes an information bottleneck, as information flowing through the network cannot travel with a one-to-one relationship. The information must be compressed in order to pass through without loss. The nodes prior to the bottleneck are commonly categorized as the encoder, and the nodes following the bottleneck are commonly known as the decoder. Autoencoders can act as compression functions, generative models, as pre-trained weights, or can be modified for classification and other tasks. Lastly, autoencoders can be trained with whatever neural network training algorithm is desired, but in the majority of studies are trained with backpropagation. Before we dive into specific autoencoder families, I want to discuss in more detail what actually happens to information as it's passed down the chain of network layers. Let's consider the following binary classification task. We want to classify red dots from blue dots, and we have one attribute to base our decisions off of. If these dots don't overlap, it's easy. We can use a one-dimensional threshold. But if the dots overlap, we won't be able to get a good accuracy rate with just this threshold. There are two things that can happen to bring our accuracy score up. The first is we add more attributes. By adding this valuable attribute y, we've increased the dimensionality of our problem, and our linear classifier might be able to correctly categorize the data. The second is we utilize a nonlinear classifier. When we use nonlinear classifiers, we don't directly add new dimensions to the data, but we do, in a sense, reshape the dimensionality of the problem. Rather than add dimensions, we warp the existing ones to form more clear separations between classes or features. While new information is not being added to the problem, we are still increasing its dimensionality in some sense. As information propagates down a trained multi-layer network, each layer attempts to disentangle the representation. At the end of the network, the information is ideally linearly separable. So if our x and y attributes contain enough information about the true distribution of the phenomena producing these red and blue dots, a deep neural network should be able to reshape the dimensionality or disentangle the problem in a way which at the final layer of the network, the red and blue dots are linearly separable. Not only do we want to form linearly separable representations of our training data, we also, of course, want to form representations that generalize to new data. We can encourage the network in clever ways to orient itself in ways which are representative of the true distribution. I'll be explaining a handful of these methods next. One challenge of training autoencoders is the avoidance of narrow mapping. By narrow mapping, I mean the translation of input to output without learning actual features about the data. Rather, essentially just memorizing the data and copying it. Given that a traditional autoencoder uses reconstruction error as its feedback mechanism, an autoencoder can learn representations in this narrow way without consequence. One technique which can mitigate this issue is the injection of noise into the input while maintaining the expectation that the model output the uncorrupted data. By adding noise into the input and expecting the noise to be removed, the model cannot minimize its loss simply by copying the data. As a result, it's encouraged to form representations that consider features about the data. Another method of avoiding narrow mapping is to encourage the network to develop similar latent representations for similar inputs. If a network's hidden layer activations differ largely for similar inputs, this is a sign that it's not learning features, but rather memorizing inputs. We can include the derivative of hidden layer activations between inputs in our loss function. Similar inputs should produce similar activations. Dissimilar inputs should produce dissimilar activations. This method is named contractive because its objective is to contract activations for a particular feature to a particular group of neurons. We can encourage the network to organize its activations further by adding in a cost per activation. With this added cost, networks are encouraged to use fewer neurons for each input propagated through the network. In order to utilize fewer neurons, the network must learn representations which selectively activate neurons based on attributes provided in the input. Given this selection, the network becomes more likely to separate groups of neurons for separate features. The final family of autoencoders that I'll cover is the historically popular and effective variational autoencoders, or VAEs. VAEs provide a probabilistic take on latent space representation. A VAE encoder receives input just like the previous autoencoders, but rather than outputting a single set of values, the encoder outputs a set of means and variances, which combine to form a set of probability distributions. The decoder takes these distributions and recreates the input to get the reconstruction loss. In addition to the reconstruction loss, a KL divergence value between the encoder's output and a normal distribution is also added. This KL divergence value will always be positive, and as a result, encourages the encoder to produce more normal-like latent distributions. By enforcing a normal-like distribution for each attribute, the latent representations for the same features are grouped more closely. As with previous autoencoders mentioned, this grouping is ideal because it leads to representation of features rather than memorization of data. One drawback of VAE's normalization is that the distinguishment between noise and detail is often lost. In the next and final video of this series, I'll be covering GANs, which are generative models that don't suffer from loss of detail in the same way VAEs fundamentally do. If you got something out of this video, please give it a like, and any feedback is appreciated. Thanks.